Hi, this is Ben Rohr, and this is ADJ.1 Problem 1. So we're going to start with the problem statement. I'm just going to go ahead and read that directly. Different operating system structures offer both benefits and drawbacks over one another, and it's important to understand what kind of structure should be used for different use cases. Consider the following situation. You are designing an operating system for an interstellar probe that is meant to run for hundreds of years. The probe should also support monitoring many specific instruments. What structure, simple, layered, microkernel, or modular, should we choose for the kernel? So let's start with some background. Let's go through each one of those structures, starting with simple. Simple is the simplest one. It has very little overhead for design and implementation. It's good for hacking it together, right? It's ideal for systems that aren't prioritizing security and don't have a lot of time restraint, right? If you have something that you need to get done quickly, a simple structure or organic structure is going to be ideal. The layered system is like a step above the simple. Well, actually, before we go on layered, simple, each level of the system, like user system stuff, all the way down to the drivers and then the hardware, all have direct access to the BIOS and drivers. So, which is fast, right? Because they can have direct access, but that also can lead to some serious problems because there's nothing stopping them from, from user space stuff, altering system stuff that probably shouldn't. So low reliability and security for that. The next structure is layered. And so it's like a step above that, right? So instead of having everything have direct access to all the way down to the hardware, you have layers. So you have like your user space stuff, and then, like maybe like graphics or something like that, down to system level things. And each one of these layers, right, can communicate with the next layer down to the hardware. So it's slow, right, because you can only get to the lower level stuff through a chain of events, right? So you get more reliability because of that, but you lose a little bit of quite a bit of performance. It's a slow system. It's good for portability too, though, because you can swap out that user space, that highest level of abstraction, easily, and use the same like internals, right, and change for a different system. Then microkernel. So that is a system where you have the core unit of it controls like the CPU, and then it has different system level stuff. And basically what you do is in like input output monitoring. And so what the idea of the system, right, is you have this very base level, very simple system where everything you connect to it is basically a plugin. And so it's a pretty highly adaptable system. And so all these different plugins for like, so if it's a computer system, you'd have your keyboard and your monitor and your different things, your whatever. And so these all communicate through that microkernel. And then through that, they can communicate with one another. And then to get CPU time and things. So that's a highly reliable system. It uses message passing. And it's very good for having multiple devices, right? Because of that architecture of having it basically adapt to different plugins and have a simple structure in the center to have it all go through. Modular is similar to that microkernel structure, but the main difference is that instead of plugins, you'd call it modules, and those modules that are all connected to that very low level system, instead of using like message passing through the system to communicate with one another, they have direct communication, which is fast. I mean, that's as fast as it gets. Everything can communicate with everything, but that comes at the cost of reliability, right? There's no watchdog making sure that things aren't communicating in bad ways or at the wrong time. So that's the basic background of each of those. So let's go through some assumptions. The system needs to work for 150 years, right? That's just taken straight from the prompt. So that system needs to be very reliable. It's also an interstellar probe. This is not something that's going to be launched and then returned to Earth or something like that. This needs to, like, we can't just pop it open and fix some kind of problem, right? So we need to make sure that the system, when it's launched, is ready to go, and that there's not going to be any significant problems. And based on the prompt, it doesn't appear that there's any major time constraints. I mean, given that the thing is going to be in operation for hundreds of years, potentially, I would assume that we have ample time to design and implement this system. Requirements. So once again, reliability is very important. It also needs to manage many devices from as stated in the prompt. It needs to be maintainable. So in that, like, the only way we could maintain it is remotely. And since it's going to be going for potentially hundreds of years, we need to have remote access to make sure it's maintainable. All right, so justification methodology. So the way we're going to do this is we're going to break up different types of functionality of the system and make sure that and we're going to compare each one of the possible structures and on a weighted scale. And so the first one at 40% is multiple device management. This probe, the purpose of it is to collect data in space. And in order to do that, it has to have lots of instruments doing this all at once. And so that's the highest priority at 40%. We have to have low potential system crashing because we can't have the system completely crash in space, because then we have a multi-million-dollar space probe that's just floating in space, and we can no longer have it if it crashes, it fatally crashes, right? Performance is another important one, because in order to get reliable data in a reasonable amount of time, it needs to be able to process things at least somewhat quickly. So that's at 20%. And testing and debugging as well is very high priority. It's listed at 10%. The main reason that we've included this is that because of the nature of the project, and that once it launches, it has to work. It needs to be testable. We need to test it. It needs to be given the green light because of the cost to do something like this. So analysis. So in the slides, we have a table, and each one is given a score from 1 to 10, and then on that weighted scale, a result is calculated. So I'll just give a brief overview of what the table has here. The simple scored the lowest overall, just because it just isn't. It's just not the kind of system that you would employ for this kind of thing. There's a very complex, high security system. Layered also scored relatively low. It got better marks than simple in most things except for performance. There's a little bit of a drop. Yeah, but it's, once again, it's a slow system. It's not necessarily great at handling lots of different devices too. That was really a big problem with it. And then we have microkernel and modular, which both scored very high in everything. But the biggest things we got from microkernel was a lower possibility of crashing, which was highly weighted. Multiple device management, they both had top marks for. Performance went to modular, but testing and debugging also went to the microkernel because of that simplicity of that internal structure. So our design decision should be to go with the microkernel. It's really the ideal situation here because we have lots of devices we need it to be highly reliable. And given that our assumption that we have plenty of time to have this, to make this and implement it and design it, there's no reason why we shouldn't employ microkernel. The other option would be modular, and although we'd see a boost for this, I think that the reliability and maintainability of the microkernel outweighs that performance. So yeah, design decision would be to use the microkernel. Thanks.